Good morning, honorable speakers, distinguished guests, ladies and gentlemen. Today is the day that we all have been waiting for. Welcome to the first day of the main event of International Seminar on Chemical Engineering Suhadi Reksawardoyo, known as STKSR, in conjunction with Symposium on Photocatalyst and Photocatalysis, known as Symphosis. This year, STKSR takes the theme of Circular Economy for a Better World. I'm Fatur, student from Department of Chemical Engineering, Institute Teknologi Bandung. It is a great and honorable chance for me to be your master of ceremony in today's event. On behalf of 2020 STKSR-Symphosis Committee, I would like to extend a very warm welcome to all of you. We appreciate you taking time off your busy schedules to join us today. First of all, I would like to thank our sponsor and supporters for helping this event to come true. The 2020 STKSR-Symphosis is sponsored by PT Energi Manajemen Indonesia Persero, Kurita Water and Environment Foundation, and PT Rekayasa Industri. This event is also supported by the ITB Chemical Engineering Alumni Association, Badan Kejuruan Kimia Persatuan Insinyur Indonesia, and the ITB Chemical Engineering Student Association. I would like to start this event with the national anthem Indonesia Raya. Ladies and gentlemen, please rise. Ladies and gentlemen, please be seated. Next, I will convey the health and safety regulations in this pandemic condition. If you're outside the house, then 1. Participants must use masks and other personal protective equipment. 2. Participants must keep a distance of at least 1 meter from other people. Then, I will read the rules of conduct during the event. Participant rules. 1. Participants are not allowed to turn on the mic and camera during the event. 2. Participants are only allowed to ask questions through the chat room in Zoom or YouTube from the beginning of presentation by speakers until the end of question and answer session. Now we are pleased to have an opening remark from Professor Chandra Stiadi, the chairman of STKSR-Symphosis 2020. Professor Chandra is currently the head of the Center for Environmental Studies, Institute Teknologi Bandung. He is also a professor of bioprocess technology and environmental policy and a lecturer from the Department of Chemical Engineering, Institute Teknologi Bandung. Professor Chandra, the time is yours.
Good morning, everybody. And probably good days, distinguished guests, rector of ITB, plenary speakers, invited speaker, colleagues, friends, and students, and ladies and gentlemen. Good morning or good day to you all. On behalf of the Organizing Committee of International Seminar on Chemical Engineering Suhadi Reksowardoyo, or we call it in Bahasa Indonesia STKSR, it is my honor to welcome you all to this seminar. STKSR is an annual seminar held by the Department of Chemical Engineering ITB in honor of Professor Suhadi Reksowardoyo contribution to early development of chemical engineering higher education in Indonesia. In this event, Professor Suhadi Reksowardoyo's sons attend this seminar. I would like to thank to Dr. Iman to attend this seminar. This year, STKSR 2020 is held in conjunction with the symposium of the on photocatalysis and photocatalysis or Symphosis 2020, organized by the Indonesia Photocatalysis Society. The topic of this seminar is the circular economy for a better world. As we may all aware, the growth of the industries play a vital role in the growth of the economy. However, along with the development of industries and economies, issues of resources depletion and environmental degradations become our main concerns. So that from this issue, the term of circular economy now is getting popular. In a circular economy, a system is built in which resources become in a cycle. Thus, we are trying to eliminate the waste produced and minimize the resource exploitation. As a country blessed with the rich ecosystem variety, Indonesia should and will fight on preserving and improving the environmental quality to pass it on to the future generation. And ITB will play a major role in that subject. This year's seminar is also very special to us since it is held virtually. The current pandemic condition causes us to limit our physical movement. And we hope that everyone here will stay in a healthy condition. However, this pandemic should not limit us to disseminate our knowledge and our networking and our connection. So the development of technology and human capability, we may adapt that the virtual conference has become a great solution for us. But we hope that the pandemic will over soon and we may meet each other again. We currently receive around more than 110 abstracts, and also with the invited speakers and plenary speaker altogether become 127 speakers from 10 different countries, and also 200 participants join this conference. It is showing great enthusiasm and passion to spread the knowledge. And we are very thankful to all the participants in this difficult situation. This number is better than we expected. Finally, the committee also very thankful to our sponsors for supporting this seminar. And myself personally thank to all the committee members, plenary and invited speakers, oral speakers, and participants for making this virtual conference a great success. I hope all of you enjoy this seminar and get many insight on the topic presented. So I would like again to thank you all and also to the rector of ITB to open this seminar. Thank you.
Thank you, Professor Chandra, for that wonderful remarks. Now we are pleased to have an opening speech from Professor Dr. I. Gedewanten, the Vice Rector for Research and Innovation, Institute Teknologi Bandung. He is a professor in membrane technology and also a lecturer from the Department of Chemical Engineering, Institute Technology Bandung. Professor Wente, the time is yours.
Hi. Halo.
Yeah, Pak Wenten, please.
Ya, suara saya jelas.
Yeah, it's. But it may be the video, you may turn off the video because your connection is not.
Oh.
Pak Wenten?
Ya.
I think I cannot hear your voice.
Halo,
Yeah.
Pak Chandra.
Yes.
Can you hear me now?
Yes.
Oh, yeah.
Great.
I just switched my connection.
Okay.
Okay, I'm sorry. Yeah, good morning, everybody.
Morning.
Yeah, on behalf of Institute Technology Bandung, it is my great pleasure to welcome the honorable keynote speakers. Oh, problem again, eh?
It's okay,
Yeah.
Pak Wenten. Yeah.
It's okay now? Yeah.
It's
Okay. Yeah. On behalf of Institute Technology Bandung, it is my great pleasure to welcome the honorable keynote speakers, presenters, and participants of the International Seminar on Chemical Engineering Suhardi Rekso Wardoyo, or STKSR 2020. This year, the seminar is held in conjunction with Symposium on Photocatalysis and Photocatalysis, or Symphosis 2020. The STKSR is a distinguished annual event held by Department of Chemical Engineering, Institute Technology Bandung since 1991, where researchers, technologies, and experts around the world share their knowledge and practices in chemical engineering field. This year, the theme of seminar is Circular Economy for a Better World. The circular economy arises from a concern of limited resources and abundant waste accumulation in the linear take, make, and dispose model productions. In the circular economy, the effective use of resources is enhanced, as well as the technology to reuse the waste in the next production cycle. The procedure is mimicking biological ecosystem. The wise of using Indonesia natural resources based on circular concept is the major target we need to achieve together through this seminar. Marking its first event on Symposium on Photocatalysis and Photocatalysis, or Symphosis 2020, we happily welcome the Indonesian Photocatalyst Society, or known as IPOS, as a collaborating organizer. The IPOS is a collaborative platform for Indonesia researchers, practitioners, and government to spread and discuss recent information and policy in photocatalysis development and application. We have confidence that the development on photocatalysis will support the circular economy in a sustainable manner, such as in waste treatment, carbon dioxide reduction, and solar energy utilization. Therefore, we support scholars and professionals to share their knowledge and innovation in the STKSR-Symphosis 2020. We believe that this seminar will bring fruitful discussion and collaboration. Together, we are shaping the future of the circular economy. Last but not least, we would like to express our gratitude and appreciation to our sponsor, collaborators, committees, and participants who greatly contribute to the success of STKSR Symphosis 2020. Hopefully, this event brings you all the best results. Thank you.
Thank you, Pak Wenton.
Thank you, Professor Wenton. That was a wonderful speech. Now, I will introduce the profile of today's plenary session's moderator. This plenary session will be moderated by Dr. Roni Purwadi. Dr. Roni is an associate professor in Chemical Engineering, Institute Teknologi Bandung. He is also the head of Department of Food Engineering, Institute Teknologi Bandung. Now, without further ado, I would like to invite Dr. Roni to begin the plenary session of today's event. Dr. Roni, the time is yours.
Okay. Good morning, everybody, ladies and gentlemen. I would like to welcome you to the first plenary session of International Seminar on Chemical Engineering Suhadi Reksawardoyo in 2020, and also a symposium on photocatalysis, catalyst and photocatalysis in 2020. My name is Roni Purwadi, and it's my pleasure to be a moderator for the first plenary session today. We have Professor Vigneswaran from Civil Environment Engineering, University of Technology, Sydney, Australia. Do we have Professor Vigneswaran today? And second, we also have Professor Bunso Otahni from Institute of Catalysis, Hokkaido University. May I introduce you, Professor Vigneswaran? So Professor Vigneswaran is a member of University of Technology Sydney, and he is expert in the membrane system in water reuse and desalination. He awarded the Distinguished Fellow of the International Water Association and also a Secretary of International Water Association Specialist Group on the rainwater harvesting. The second one is Professor Bunso Tani. He is come from Institute of Catalyst, Hokkaido University, and he has publishing about 300 original paper with the H index 69 and the second single author book and 2 single author book. His expertise is photocatalysis, and he awarded the scientific achievement on Electrochemical Society of Japan, and also the Japanese Photochemistry Association Award in 2006. Okay, for short, we welcome Professor Wigneswaran. Professor Wigneswaran will deliver a lecture about alternative water source toward water security. During a lecture, a participant is forbidden to interrupt, but if you have any question, please write your question in the chat room. So the moderator will rewrite your question and will be shown in the end of this lecture for a discussion. Professor Wigneswaran, time is yours.
Good morning.
Good morning.
Good morning. I wonder whether you are going to press. Okay, thank you so much. Good morning.
Good morning, sir.
Good morning.
And I thank the organizers for giving me an opportunity to speak in front of you all, and especially Professor Sandra Settiadi, who has been associating with me for the last 35 years or more, and still we are collaborating. So the topic I'm going to talk today is on the alternative water sources towards the water security. And I will bring some examples on the circular economy during my talk with the case studies which we have conducted. It's not moving. Okay. Next slide. It's not moving, please, sir. Okay. So by 2025, 1.8 billion people would inhabit in areas affected by the water scarcity. About 2/3 of the people will live in water-stressed region. These are the results of excessive water usage, population growth, and the climate change. Okay, so next slide, please. So I am going to speak on the desalination, water reuse, and the stormwater, especially on the aspects of water, alternative water, and resource recovery. Next slide, please. In Australia, we have got 8 large desalination plants and more than 600 small desalination plants. Next one, please. So the desalination process is fairly simple. After the sand filter or dual media filter and security filter, cartridge filter, the seawater enters into the reverse osmosis plant in 2 passes, and we get the desalinated water. The main problem here is more than 50% of the water we put through the reverse osmosis comes as the reverse osmosis concentrate, which affects the water quality, especially the marine ecosystem. Next one, please. So what I am going to talk today is how we can recover the valuable metals from the reverse osmosis concentrate and offset the cost of the desalination, because desalination is supposed to have a very high the maintenance and operating cost, and also contributes to the global warming. Apart from the sodium, magnesium, and other common inorganics, we have many metals such as lithium, rubidium, and also rare earth elements. And if you take the rubidium, the amount of the rubidium is almost similar amount of lithium. Lithium is mined very frequently for the usage in the batteries and similar purposes. Rubidium also has many uses, but the advantage of mining the rubidium is the cost is about $1,500 per kilogram, about 100 times more than that of lithium. Next one, please. So what we did was, we used the membrane distillation coupled with the adsorption. Here we used the copper, potassium copper ferrocyanide, and we granulated the adsorbent using the polyaromatic polyacrylate nitrile to make into granules about 1 millimeter or more, not to block the pores, and by which we could able to get 65%, additional 65% of the clean water, additional water, and more importantly, 98% selective rubidium. We can get 98% rubidium in a pure form, and we achieved that one by air stripping method. If you take the economics, even in very small plants, we can get about $8 million revenue by recovering 700 kilograms of rubidium per year, after deducting all the operating cost and the cost for the machineries. So one advantage of this, by recovering this, we can use the rubidium for other purposes. At the same time, we can offset the cost which will be incurring in the desalination plant. Next one, please. Next one. Now I'll move to the water reuse. Water reuse is becoming a very important issue in many countries, especially for non-potable purposes, such as watering the garden and other non-potable. We don't need to use this reused water for drinking purposes. In Singapore and other places, also in Australia, water reuse is one of the major issues for the non-potable and industrial uses. Next one, kindly. In Sydney Water, we are using about 70 billion liters per year. As of 2015, now it has increased to 85 billion liters. So the percentage of reuse is increased from 12 to about 20%. And this water is used for the non-potable reuses. It is mandatory or important. All the new towns have to use the recycled water for their non-potable resources. And as a result, there will be reduction in the amount of drinking water going into the system. Next one, please. If you see the market, membranes earlier have been used as the post-treatment after the biological and tertiary treatment, and the market from 2006 to 2010 rose by 33%, from 2.1 billion to 3.3 billion. But when you take the membrane bioreactors, the increase was, during this time, the increase was about 4.5 times, or it increased by 450%. In China alone, in 2015, 28% of the plants are using the membrane bioreactors. Next one, please. Membrane bioreactors are now used in a very, very large scale. For example, in very, very large towns in Indonesia and other Southeast Asia countries also can be used. For example, the latest example is in Sweden, is in Stockholm. They commissioned this plant in December 2019. The design capacity is 864 megaliters, which is 864,000 tons per day. So similar plants are available in France, USA, China, and so on. And there are many thousands of smaller scale membrane bioreactors are available worldwide. Next one, kindly. In Sydney, we were involved in a membrane bioreactor study in a small town called Castle Hill sewage treatment plant. By using the big data and also by using the feedback system from the pressure sensors, we optimized the backwash duration, and also we optimized the frequency of backwash. Earlier, every 18 minutes it was backwash. Now, it is not necessary, even sometimes for one day, no need backwash, because if the water quality is good. So it depends on the water quality. It senses the backwash frequency and the amount of time by which we could able to reduce about 70% of the water used. So we could able to, by using the powder activated carbon in the system, we could able to even lower the capex cost. Next one. In Sydney, there are about 25 inland treatment plants, apart from the about 4 major ocean outfalls. The 3 major inland plants are in Penrith, St. Mary's, and Quakers Hill. Before 2010, we were discharging after the biological treatment and tertiary treatment, we were discharging into the creeks. And Warragamba Dam had to put some water into the Nepean River for the agricultural purposes. Since 2011, these 3 plants, the water already treated, going through the advanced water treatment plant, and it is treated further and it is going to the Hawkesbury Nepean River. So there is no need the water coming from the Warragamba Dam for replenishing the water. Next one, please. So here, as you could see, the treatment system in the advanced treatment is the ultrafiltration and reverse osmosis. And it treated about 50,000 meter cube per day. And these plants, about 85% treated water, now it's going back into the Nepean River, and this can be used for the agricultural water reuse. However, we are still having about 7,000 meter cube per day of concentrate, which has the microorganic pollutants and other pollutants, which has to be treated before discharging into the rivers in the long term. Next one, please. So we made a study on the reverse osmosis concentrate. Next one. We chose a small treatment plant in Sydney Olympic Park, where they have, after the biological treatment, they use the sequencing bioreactor. It goes through the microfiltration and reverse osmosis. Still, although this plant capacity is about 5,000 meter cube per day, they are discharging about 300 tons per day of water into Parramatta River. And this leads to the micropollutants and the pharmaceuticals into the Parramatta River. And in the long term, it is not acceptable. Next one, please. So we made this study. Next one. So this is the Olympic Park treatment plant in the glass house. And what we used was, we used the ion exchange and the adsorption in series. In fact, in ITB, you all are working on the economically viable adsorbents and ion exchange. They also can be used for this purpose. Next one. So as you could see here, they could able to remove practically all the micropollutants, including the pharmaceuticals, almost 100%. So the Parramatta River quality will not be affected in the long term. Next one. We also studied, instead of using the reverse osmosis, is it possible to use the nanofiltration alone, or together with the reverse osmosis, nanofilter as the first pass and reverse osmosis as the second pass. Next one, please. Next one. Next slide. So we used nanofilter as a first pass, and only 50% of the water treated by nanofilter is going to the reverse osmosis, and they are blended together, and this water is sent to the Parramatta River. Next one, kindly. So here, nanofilter alone can remove majority of the pollutants, and the remaining may be removed by partial operation of the reverse osmosis. The advantage of this system is it removes all the nanofilter, removed all the inorganics necessary except for part of the sodium and the chlorine. And after, next slide, please. So by blending 50% of the nanofiltered water with 50% of the reverse osmosis, we could control the chlorine and the sodium for the agricultural uses, and also the sodium adsorption ratio, which is a ratio used by the agriculture specialist, to below 8, and the standard is 14. So we can obtain a good quality water by using the nanofilter, and also we can reduce the cost. More importantly, next one, please. More importantly, as you could see here, when we use the reverse osmosis alone, we have severe organic and ultimate biofouling. Whereas when we use the nanofilter, we can reduce the biofouling on reverse osmosis significantly. So the operational cost and the biofouling can be significantly reduced by the use of the micro nanofiltration. Next one, please. Next one. Okay. Now I will discuss the phosphorus recovery. The phosphorus is a very important aspect, and since 1950s, they are taking the phosphorus from the phosphorus rocks, which comes from only 3 countries, from USA, Morocco, and China. And the amount of phosphorus fertilizer will become more and more important, because when the food production increases by 70% in 2050, when the population increases to 9 billion. So phosphorus is a very important aspect. Next one. So nowadays we are discharging the phosphorus into the rivers, which leads to algal blooms. Why not we use the sewage? In Sydney alone, we have about 1,200 megaliters, or 1,200,000 tons. And on an yearly basis, even if you assume a very low phosphorus value of 10, we can get about 4,800 tons of phosphorus annually. So we don't need to rely on the phosphorus rocks. And in the meantime, we also avoid the problem of the eutrophication or algal bloom. Next one, kindly. Next. So we can recover the phosphorus by biological process, although it is environmentally friendly, more complex. People use the struvite or apatite fertilizer formation. Next one. So we worked in a plant in Gordon in Sydney, and this plant is very small, only 110 megaliters per year, or 110,000 tons per year, very small plant. And this uses the anoxic and aerobic zone as a biological treatment, followed by the ultrafiltration. And here the water is 98% of the water is collected and reused for the irrigation. On the other hand, next one. Next one, please. Oh, the one before. Yes, thank you. But the one before. Earlier slide. Earlier slide. Yeah, the one after. Next one. Oh. Okay, I think there's something missing. It's okay. So it's about 1,010 megaliters per year in this plant, which can treat about 4 metric tons per year of phosphorus which is sufficient for the nearby places. Next one. Next slide, kindly. Thank you. And what we used was, we used the ion exchange. We absorbed all the phosphorus and then desorbed, and we added the lime to make the apatite fertilizer, and we added small amount of magnesium chloride and ammonium sulfate to make the struvite fertilizer. Next one, kindly. Next slide, please. So when we analyze the composition, you can see, please, the composition of the phosphate, ammonium, and magnesium were almost similar to the commercial values. They were similar to the theoretical composition of struvite and also the commercial value. So we can, without any problem, we can reuse it as a fertilizer. Next one, kindly. Next slide. So the next one is the stormwater harvesting. We worked in two major plants. One is in Blacktown, is one of the largest towns which is expanding. And this is one of the stormwater harvesting systems, Angus Creek. So you can see here, this collects about 200,000 tons or a meter cube of stormwater every year, this particular small harvesting system alone. And this water, we made a continuous assessment on the quality by using the automatic analyzer, and then we can use it for the soccer grounds. There are about 16 soccer grounds operational. Then they want to put another 24 soccer grounds. This water can be used. And more importantly, this stormwater, as you could see, this stormwater otherwise causes the flood problem. And if we don't harvest it, it will go as a waste. And stormwater will not have any objection from the people also. Next one. And in another small council we were working, Gurungai Council, they have 16 harvesting sites, small ones. And from the stormwater line, it is going through the biofilter, a simple biofilter, and the water is collected. And only occasionally if it contains the microorganism, otherwise the microorganisms coming out is very little, and it can be used to irrigate the nearby fields. They have about 16 fields, and this tank size is only about 400 cubic meter tank size. Next one, kindly. Next one. So in the northwest or in the west part of Sydney, there is a great increase in the urbanization. For example, there are about 70,000 new houses being built, for example, alone. So they have two stormwater facilities. One is from these houses, about 30 hectares from the low density urban catchment. And another one is about 6.6 hectares of low density. And as can be seen from these are from the houses, and they are building the bioretention tanks. Bioretention tanks. This is bioretention 2 and this is bioretention 1. There are two. Next one, kindly. Next one. So we are working with the council. They are using some cost-effective medium to fill the bioretention tank. We have to see the life cycle of the medium. And we have to also see whether they can remove the polyaromatic hydrocarbons and other nutrients, excess nutrients. So we are making a study using a simple permeable pavement arrangement to see the usage of this medium in removing the necessary pollutants, and also how long they can operate, 10 years or 15 years, and what we can do after this sand or medium become exhausted. So this study is going on, and this is very important. Next one, kindly. The more important one is the high rate systems. Now with the urbanization, we have very little the sand area or grass, and practically all the water goes as a storm water. And this storm water, for example, in a Carlton stormwater harvesting facility, which we worked on, from the stormwater canal, it is collected and we treated this water by a simple system, and we stored this one in the storage tank, and we provided this water to the construction industry across the road. That way, the construction industry does not have to pay for the water. Next one, kindly. So in this system, we used simple filters. This is in a cubicle of only 2 meter by 2 meter, a small system, as you can see. And then, if necessary, we can use also membranes, which is in most cases is not necessary. And this is the storm water coming. And as you could see, during the major storm events or major rain events, a lot of water is flowing through, which otherwise lead to flooding problem or the wastage of the storm water. Next one, kindly. So what we propose to the council, Gurungai Council, Kogra Council, after the filter system, the water is stored in the storage tank. We can use the membrane filter, which operates the gravity of the water head, and also it can be cleaned by the water level in the filtrate tank. It can automatically also clean the membrane. Now the council is using, instead of the membrane, we are using the back filter, a similar back filter, to remove some of the pollutants which were not removed by the high rate filter. Next one. Next one. So I will end the talk. There are major problems, safe water, especially in the rural and isolated areas. Always the rural areas and isolated areas are forgotten. For example, 137 million people are affected worldwide by the arsenic contamination from the groundwater. 52 million people in India alone is affected by fluoride. In Australia, in Western Australia and other places, there are many isolated areas where they have no proper water source. And we worked in one of the areas where the clean water is available only 800 kilometers, not meters, kilometers away from these areas. So we do have to give some water from the water source they have got. For example, they have only 3 groundwater, and the water quality is much worse than the seawater. And there are many countries, including the Central Australia affected by the nitrate. So we all have to find ways to remove these, and also in some cases we can recover the nitrate and fluoride, for example. Next slide, please. Next one. We were funded by the Google to work in a Red River Delta in Vietnam. The red color shows the very, very high concentration of arsenic, and more than 4 million drill wells alone in the Mekong River Delta. So there are about 20 million people are affected by the arsenic pollution in Vietnam alone in the Red River Delta. Next one, kindly. Next one. Next slide. Next slide, please. So we, in the project, we proposed about the many systems for the play schools in Vietnam. The play schools are very big, the sense about 500 children aging from 1.5 to 5 years, and they need good water for the drinking and also for the food they consume during their stay during the childcare. And we made a system which costed only about the media is less than $45, and we replace only once in 6 months. And other than that, this is the only replacement cost, about $90 per year for a big capacity, but the treatment system is only less than about $500 to $1,000 only. Next one, kindly. So we also put the systems for the houses where they don't have any alternative water. The houses which are a little bit rich, they have a better system where it contained few 2 or 3 adsorption medium filters inside. And for houses, this costs only about $85. And for the houses where they don't have the money to pay, they can have a simple system which costs only $20. And this one can give good quality water for their drinking purposes. We tested for over 2 years, and these filters are working without any problem. So I will conclude with this. So what I was trying to say is, in addition to the alternative water sources such as stormwater, water reuse, and desalination, we also can recover some very useful materials such as rubidium, lithium from the seawater, phosphorus and nitrogen from the wastewater, and stormwater. Of course, we can get a good quality water and we can have a sustainable system. Thank you so much.
Thank you for your lecture, Professor Vigneswaran. Now we come to the discussion session. I think the committee has collected the question from the chat. Can you show the question? I saw some question here. Yes.
Okay.
Okay. The first is from Professor Chandra. The question is for Sydney water reclamation. Is there any plan to use the reclaimed water for the domestic or industrial usage? And second one, Professor Vijay, what is the most important things to be considered when we want to reuse stormwater? As many cities in Indonesia experience flooding annually. So this is the first two questions. I hope Professor Vijay can explain more detail and answer this question.
Okay, thank you so much. For the first question, the reclamation, yes, about 20% of the water is recycled, and it is mandatory or compulsory for the new towns they release. They have to use for the non-potable or non-drinking purposes. They have to use the reclaim water. This is mandatory. Okay, and industries, yes, in some towns they also can use it for the industry because which is beneficial. One example for the industry is a power plant in Eraring near Newcastle. Earlier, they needed about 5,000 tons per day of a very demineralized water. So even the drinking water, they have to go through the reverse osmosis and ultrafiltration to remove all the minerals for the use in the power plant. So what they are doing in Eraring plant is they are using the reverse osmosis from to treat the. There are about 10 sewage treatment plants. They are using only the one treatment plant, Dora Creek. They take their water and treat that water by using the reverse osmosis and use it for the power plant. This has many advantages. Otherwise, Dora Creek sewage treatment plant effluent has to go into the estuary. So they need to build a 15-kilometer pipeline. So now they don't need it because the water is used by the power plant. So like that, and also Hunter Water does not need to make another drinking water treatment plant because now they are using the water from the sewage treatment plant. So water reuse is also very, very beneficial for the industry use, and especially when they use this one, the return cost, for example, in Eraring plant, a power plant, they could able to recover the capital cost within 3.5 years. Then after 3.5 years, they are getting a saving about close to $0.9 million because now they don't have to pay for the water because they are taking the water from the sewage treatment plant. Yes, as Professor Sandra mentioned, yes, the reclaimed water is used mainly for the non-drinking purposes. In Singapore, yes, they are also promoting for drinking, but I feel it is not necessary for social and religious beliefs. We don't need to focus on the drinking purposes. We can always use for the non-potable purposes. Non-potable purposes constitute about 80% of our water usage. Sandra, are you satisfied with your answer?
Yes, thank you, Vijay. Please.
Okay, so now the second question is what are the most important things to be considered when we want to reuse the storm water? Yes, the storm water, we have to plan it very carefully. One of the main problem with the storm water is the flooding. We have to put the harvesting systems at appropriate locations in equally, by which they can reduce we can't completely avoid the flooding, but we can reduce the flooding issues. And another important thing is I think some of the universities, together with the universities in Indonesia and also NGOs in Indonesia, they worked when they had a flooding in Aceh, I suppose. Yes. So what happens is the water quality. Water quality becomes an issue, and their drinking water and other potable water is affected by the flooding. So during that time, we also have to have emergency filtration systems to avoid this problem. For example, we now, although we are working only in the arsenic thing in Hanoi and Hanam provinces, in central Vietnam, as you might have heard, there was a huge flooding and people were suffering from the lack of drinking water. There was a lot of waterborne diseases. So you had to have some emergency filter or emergency treatment systems in mobile emergency systems or some emergency systems in place. Okay. So your question, this one, flooding, we have to work together as a team, the hydrologist, water quality people, and water treatment people. All three have to work together. The one is the urban water management to control the flooding. That's one of the important things. Then one comes to, then part of the problem can be mitigated by having a stormwater harvesting system. And then during the major flooding, the water quality is a huge issue. So the water, the people have to build some emergency systems. I do not know whether I answered your questions.
Yes, sir. Thank you very much.
Okay, I think your explanation is quite clear.
Yeah. So there are a few questions more. Or you want to answer them?
I think because of the time, I think you can answer the
very briefly.
First question. The first is from Professor Sasongko.
Okay.
He asked about the current price of residential drinking water in Sydney.
Okay.
Second,
about sorry. About
yes,
$2. About $2.
It's per liter or per
ton, per meter cube.
Per meter cubic meter,
okay.
Yeah.
Yeah, and and also the reuse water also cost not as high as $2, but less. But government and the Sydney Water gives subsidy so that people will start using the reuse water.
Okay.
Okay.
The next.
And yes,
please.
Is since yes, is 0.2 parts per million. I agree, it's very small, but it can be this 0.2 with the adsorbent. Very small amount of adsorbent can be removed completely. Okay, so even the lithium, they are recovering. That also has a very small amount, which is less than 0.27 parts per billion. Okay, so I understand the question because when you see this value, you always see so it's very little amount, but the price is very, very high. Okay,
yes.
And when one small answer is the purity. When they use the land mining, when you use from the land, they need to purify 30 steps. Whereas when you purify the rubidium from the seawater, you need less than 4 steps. So that's another advantage. And also seawater is a large amount.
Yes. Can you answer the third
Last
question?
question. Yes. Does has the standard on or on what technology should be used? Okay, it's a good question. Yes, they have a standard. The standard is put forward by the EPA together with the water authorities, and it depends on the usage. If it is for drinking, it is more stringent, more strict. They have a standard, and more than standard, they are now forced to have the reverse osmosis. Earlier, they had only the microfiltration. They want to have a reverse osmosis to make sure all the pollutants, especially the the microorganic pollutants, are removed. Okay, and the salts, for example, when the salt also coming, so that also can be removed for the agricultural purposes. Agricultural purposes, you can't have a larger amount of sodium, potassium, and chlorine. Industry, they can choose the process, but it is the ultrafiltration and reverse osmosis, but they can change a little bit, but they do have to get permission, or before they run, they have to get the permission, or the EPA has to endorse the process and the quality of water.
Okay, thank you, Professor Vijay, for the nice lecture and also very clear explanation and for answering the question. So now we move to to the second lecture from Professor Bunso Otani. Professor Bunso Otani is from Institute of Catalysis, Hokkaido University, and he will talk about the design preparation and detailed characterization of photocatalysts based on energy resolved distribution of electron traps. Professor Bunso,
Yes.
the time is yours.
Thank you very much for introduction. And this is the very happy opportunity for me to speak about our recent results in front of the people a number more than 100. So I'm talking about the very, very fundamental issue on material science. Okay, in any industries, we use materials. And that is also studied in academic and also in industries. And we often use the term design, synthesis, fabrication, or characterization of materials. Yes, and we do it. Design, synthesis, fabrication, characterization of materials. However, honestly speaking, this is illusion. Unless those materials are identified. It is, at least in the field of organic chemistry. As you know, the organic compounds must be identified for publication in journals. For example, this is the regulation of Journal Organic Chemistry published by American Chemical Society. and they request the identification of organic compound at least by using at least elemental analysis data within 0.3% error. And this shows the composition of organic compounds and the purity. And the skeleton, that is the structure of material, the organic compounds, is identified by using, for example, nuclear magnetic resonance spectrum, NMR. And without those analytical data, it is impossible to publish any organic compounds. Yes, this is the truth. And the NMR tells the what is the structure of material. For example, this is our results of production of fluorine from ornithine by using titanium photocatalysis. And the upper panel shows the prepared by photocatalytic reaction, and the lower panel tells the authentic sample of fluorine. And we see the almost the same patterns, and this tells clearly the structure of our product is just fluorine. Yes. And this is a very, very famous organic compounds, polytoxin. So the TOX means that is a toxic material, and that is first found in sea animal, and then that is synthesized, totally synthesized by organic chemists in Japan. And therefore, this compound, polytoxin, has been identified at least twice. And what is the meaning of identification of this polytoxin? That is the name of this compound is determined. And this is important point. So the name, this is the official name of this polytoxin, and this is unique. So any other structure can be shown by using this name. So that means this name is simply show this structure. So therefore, what is the meaning of identification is to be uniquely named, reflecting structure. So this is the one of the most important point. So that means identification of at least organic compound is made by using the nomenclature, that is naming of compound reflecting those structures. And going back to the material science, using solid material. For example, titanium oxide is one of the most frequently used photocatalyst. And what we say, those titanium oxide, the name is titanium oxide. And that means the composition is TiO2. So this is the same as the elemental analysis of organic compounds. So only the composition TiO2 is shown by this name, titanium oxide. No other information here. So therefore, it is almost impossible to identify. So every time, if the composition is titanium oxide, we say that is titanium oxide or TiO2. So even if we see the difference in structure or difference in activity or properties or characteristics, but they are called as titanium oxide. So that means we don't identify those solid materials. However, the IUPAC tells they allowed not to identify inorganic compounds. This is the one of the IUPAC publication, that is the nomenclature of inorganic chemistry. And IUPAC said that for solid inorganic material, it is, however, in cases where detailed structural information is to be conveyed, free systematic names can be difficult to construct. That means the full detailed structural information cannot be used for naming inorganic compounds. So that means we, material scientists, is allowed to not to identify inorganic compounds. However, why organic compounds must be identified for publication? The reason is very simple. Without identifications, there had been so many confusions on the discussion of organic compound without identification. So therefore, they needed to start making the identification, the necessary identification. And then for inorganic materials, inorganic solid materials, we might have the confusion on discussion without identification. So I think, at least I think, we need to identify those solid inorganic compounds, such as photocatalyst. Why the structure of inorganic compounds, solid compounds, is very, very difficult to determine. That is the reason is very simple. Those solid material has bulk structure, and probably most of you think that the bulk structure can be determined very, very easily by using XRD, X-ray diffraction analysis. Yes, if that is crystalline material, that can be. And the crystalline structure can be determined easily. However, if those materials contain the amorphous part, it is impossible to determine what is those amorphous and how much amorphous part are included in that system. And of course, the solid material has surfaces, so we must determine the surface structure. But different from the crystalline structure, the surface structure is very, very difficult to describe using text, using name. And of course, the surface structure is not uniform, and we should determine the distribution of surface structure. And even if we can determine the bulk and the surface structures, still one more property must be determined. That's the size. Even if the same bulk structure, same surface structure, still the size must be determined. Even if the same bulk structure and the surface structure, but if the size is different, the property must be different. So therefore, at least three structures, bulk, surface structures, and size, must be determined for identification, and it is almost impossible or entirely impossible to make this. So we only report the solid inorganic material, for example, crystalline phase by XRD, and primary particle size, secondary particle size, and specific surface area. And those are all bulk structures. Probably you think that the specific surface area is a kind of surface structure. No. The specific surface area is showing that only the size of surface. And even if the surface structure is different, if the particle size is the same, the specific surface area must be the same. So therefore, no information about the surface structure is included in specific surface area. But probably the old scientists know that the IR was used to identify the organic compound for the former days, for example, more than 40 years when I was a graduate student. The infrared is a very, very not so expensive instrument at that time, and no NMR were there. And the organic chemists used the IR. For example, this fingerprint region is used to identify the organic compounds. So at that time, not those patterns, higher spectral, could not be interpreted fully. So that means just a fingerprint. No meaning why those peaks are there, but the fingerprint tells that if those patterns are seen, they can be identified. So that is the use of fingerprint is one of another way to identify compounds. Probably you know him, and probably you might know him if you see this my profile, and probably they are identical. They are the same because the thin hair, wireframe glasses, beard and mustache, and the ring on left third finger, and the black turtleneck sweater, and handsome. So six parameters are same. So therefore, they must be identical. No. If the fingerprint are shown, it is possible to say they are identical or not identical. So without using those data, it is possible to identify those people by using a fingerprint. So fingerprint is very, very important. So then, if we have the fingerprint for those in organic solid material, it is possible to identify. It might be possible to identify those inorganic solid compound. And that is ERDT-CBP pattern. That might be a fingerprint of those inorganic material, especially semiconducting metal oxide particles. And without using those characterization, only by using the ERDT-CBP pattern, it is possible to identify inorganic solid compounds. That is provided by the newly developed reverse double beam photoacoustic spectroscopy, RDB path. And I have no enough time to interpret fully of this technique, but that is we assume the presence of electron traps. Electron traps is the vacant electronic state. Though we don't know what is the real structure of those electron traps, but it is possible to observe the accumulation of electrons on those vacant electronic states, electron traps, by using this technique, using the two light beam. One is the continuous light beam to excite electron in valence band of semiconducting inorganic compounds directly to electron traps. And once the electrons are accumulated in electron traps, it might have the photoabsorption. And the newly developed photoabsorption is detected by photoacoustic measurement. That is by using the modulated light and the microphone. And that is the very, very old-fashioned technique. But by using those two light beams, it is possible to make a measurement of electron trap distribution. By scanning the light beam of excitation light from longer wavelength side, that is lower energy side, to higher energy side, shorter wavelength side, it is possible to fill up all the electron traps from the lower side to higher side, that is deeper side to shallower side. And the actual the results is the top panel shows the photoacoustic signal intensity during the scanning of excitation light from longer wavelengths to shorter wavelengths. So you see the accumulation of electrons in electron traps gradually. And this is the total amount of accumulated electrons. So therefore, these the spectrum is differentiated from the longer wavelength side, the lower energy side to higher energy side, to show the energy distribution. this is the relative distribution of electron traps. So therefore, that is converted into absolute density in the unit of micromole per gram by using the previously reported total density of electron traps. And by using the same apparatus, by using single beam measurement, that we can obtain the the spectrum, something like a diffuse reflectance spectrum. And from this photoabsorption edge wavelengths, it is possible to calculate the band gap. And band gap is the energy difference of conduction band bottom position in reference to valence band top position. And the electron trap distribution is provided by the VBT as a reference. So therefore, the electron trap distribution and the conduction band bottom position can be plotted in the same plot as in the right panel. And this is the results of one of the titanium oxide, commercial titanium oxide sample. And the 152 imbalances show the total density of electron traps. So that means that we have obtained the electron trap distribution as a bar graph and the CBB position as a line at about 3.1 electron volt, and the total density of electron traps of 152 micromole per gram. That is one of the ERDT pattern data for one sample. And this is the commercial titanium powders. And A means anatase, R means rutile, and B brookite and amorphous. And those anatase with small amount of rutile and rutile with small amount of anatase, it is possible to see that those ERDT CBB patterns are all different. And but please do not misunderstand. Maybe you see that the anatase gives such a pattern and the rutile gives such a pattern, the brookite and the amorphous. No. Even if the bulk structure, anatase and rutile are same, they are different. So we have many kinds of those categories of titanium. And for example, anatase only sample gives almost the same CBB position. And the rutile only sample shows almost the same CBB position that reflects the bulk structure, anatase and rutile. However, if the anatase and rutile is mixed, the CBB position is different, showing the difference in the composition of bulk structure. And for example, for anatase sample, the left one and right one, that has the almost the same specific surface area, but the pattern is all completely different. So that means the ERDT pattern, electron trap distribution pattern, shows reflect the surface structure. So the surface structure is different. The ERDT pattern must be different. So it is proved by this plot. So this is the plot of total density of electron traps versus specific surface area. This is not a clear linear relation, but it is possible to say that the total density of electron traps are increased along with the increase in specific surface area. That means almost all the electron traps are located on the surface, and if the same titanium samples are used, the surface structure is not so different. So the density is about 1 electron traps per square nanometer. So that means electron trap distribution reflects the surface structure because the electron traps are almost on surfaces. Okay, so then this is only the part of results of titanium, commercial titanium samples, and you see that they are completely different. So different kind of TiO2 titanium sample photocatalyst sample gives a different ERDT-CBB pattern. So that means those ERDT-CBB patterns can be a fingerprint of titaniums, like NMR patterns for organic molecules. So then we check the probability of using this fingerprint for identification. So we choose one of commercial titanium sample FP6, and we carefully take a sample from the same bottle of FP6 3 times. And the results are shown here. So that is almost the same patterns. And to quantitatively analyze the similarity of those ERDT-CBB patterns, we introduce the degree of coincidences. And one degree of coincidence is the pattern shape, ERDT pattern shape, and not depending on the absolute value. So the pattern shape, if the same, that it must be 1, and that is different, that must be 0. So the value of degree of coincidence are calculated between 0 and 1. And the total density is also compared, and that is to be the value between 0 and 1. And the CBB position also checked, compared to give the degree of coincidence, zeta C, the value between 0 and 1. And by considering the standard deviation of results, we put the small weight. And the total density, zeta, total density of coincidence, zeta, is provided by multiplying those 3 degree of coincidences. And actually, the 3 pairs of those 3 samples gives the zeta value higher than 0.88. And almost all the data are above 0.9. So therefore, it is possible to say that the zeta value, if the zeta value is higher than 0.9, it is possible to say they are identical. However, if the sample is taken in the same bottle but a bit different position, that is shown as another, that shows a bit different ERDT-CBB pattern. And actually, the zeta value for this another sample with 3 samples gives the zeta value about 0.7. That is significantly lower than the first 3 samples. So therefore, this shows the technique, ERDD-CBB pattern measurement, is very, very sensitive for such a very small inhomogeneity of sample in all, even in the same bottle. Okay, so we measure those zeta values for the pairs of titanium samples, and this is only the part. We checked more than 5,000 pairs of titanium samples, but the result is almost the same. And actually, they show the data value, the low data value. Almost all the pairs shows the data value below 0.3 or 0.5, 0.4. And only limited number of pairs show the high degree of coincidence. Here, the red bars shows the higher zeta value pairs. Only 7 pairs out of 5,000 pairs shows the zeta value higher than 0.6. Here is the list of top 7 pairs, and the TiO4, the rank 2, TiO4 and the P25, TiO8, ST01, rank 3, and the rank 7, TiO11 and Fp6, they are provided the same product with different code name. So therefore, they must be the same. But the actual data value is the highest one, rank 2, 0.76, and the lowest one, 0.615. So that means even if the same product or same production lot, the depending on the production, the small difference in the production condition or difference in the condition of storage, the surface or the other kind of properties must be changed. And important point is WACO sample appeared in rank 1 and rank 4. They are very similar to TiO4 and P25, and the TiO4 and the P25 are the same. So therefore, WACO must be the P25 provided by the own name of by WACO. But the important point is to clarify this. In the light column, that is the zeta PC. That is the degree of coincidence of photocatalytic activity. That is the average of 3 photocatalytic reactions. And actually, the top rank one, that is TiO4 and WACO, gives the value of zeta PC about 0.9. That means that they show the almost the same photocatalytic activity. Yes, so that means they are the same. Not using the label or code name, it is possible to say those materials are same. To make this clear, we plot the zeta value and the zeta PC value for those titanium oxide samples for 3 kinds of photocatalytic reaction. Actually, that is scattered. Nothing can be there. No. Here is a line. So that means for the pairs of zeta value higher than 0.6, the lower zeta PC value couldn't be obtained. So every time the sample pairs with zeta value higher than 0.6 gives the similar photocatalytic activity. To make this clear, the 7-point non-weighted moving average were taken for this. And this clearly shows that if the zeta value is below 0.6, that is scattered. So sometimes even if they are different material, but they accidentally the same photocatalytic activity or accidentally different photocatalytic activity. However, if the zeta value is higher than 0.6, the zeta PC value is increasing. And if the zeta value is higher than 0.8, it is possible to say that they show completely the same photocatalytic activity. Yes. So that means we could identify those titanium oxide samples if the zeta value is the same, the zeta PC is the same. And not limited to photocatalytic activity, the other kind of characteristics or measurement results are same if the zeta value is higher than 0.6 or 0.8. So we call this elephant plot. That is a very, very new type of plot. Okay, so the minimal requisite for identification is something like that. Bulk structure, bulk surface structure, bulk surface size or surface structure. And the ERDT CBP pattern tells that the surface structure is reflected in ERDT and the conduction band bottom position is reflecting the bulk structure, and the total density is almost linearly increased with specific surface area. That means that shows the surface size. So therefore, ERDT CBB pattern can be used for identification. So then we check the photocatalytic activity, and the ERDT CBB patterns are arranged in the order of photocatalytic activity in these 3 photocatalytic reactions. And the left top panel is the highest photocatalytic activity sample, and with the activity is decreasing, and the left bottom panel is the lowest activity. And 100 means the maximum activity, and the lowest one is 6 for hydrogen evolution case. And for CO2 case, the lowest one is 10, and also evolution case, that is 1. Yes. And you see, except for H2 case, the CO2 and O2 gives the pattern almost the same if the photocatalytic activity is higher than 70%. So that means the higher activity sample for these two photocatalytic activities, photocatalytic reaction systems show the almost the same structure. So that means they are optimized in many kinds of the structures determining the photocatalytic activity. And the lower activity sample is active due to at least one or two structure is not suitable for higher photocatalytic activity. And for H2 case, there is no similarity in higher activity data. So therefore, it is possible to say that if by changing the preparation or the reaction condition, it is possible to higher photocatalytic activity samples. So in the Anna Karenina, written by Tolstoy, the first sentence of this novel is, happy families are all alike. Every unhappy family is unhappy in its own way. So then, I'd like to say, active photocatalyst powders are all alike. Every inactive powder is inactive in its own way. So therefore, that we need to change our mind for the design of photocatalyst or the other functional materials by checking this point. So now the instruments, the laboratory made instruments are open for everybody in the world. And you can measure your sample by using this technique. And at least this is only the part of the collaborators, and those people are working in those institute sent us the samples and we measured them. Okay, so the my email address is here. So if you have any request to measure your sample by using this RDB pass, please contact me. Thank you very much for your kind attention.
Thank you very much, Professor Ohtani. Now we enter the discussion session part. So I would like to invite committee to show some question regarding your presentation.
Yes.
Okay, Professor Ohtani, there is one question from Dr. Hendra. Is there any significant difference for calculating band gap energy of semiconductor? For instance, titanium oxide by comparing between ARDT CBB approach and UV diffuse reflex.
The band gap energy that is showing as CBB, that is not so different from the diffuse reflectance spectrum. And actually, even if the data on taken by diffuse reflectance is different from our measurement CBB, there is no need to think about this. So only by checking the ERDT CBB patterns of samples, it is possible to say something about the bulk structure from CBB. And as in the last part of my talk, the some correlation of ERDT CBB pattern of photocatalytic activity are shown, but that is just the similarity of patterns. And we need to accumulate the information of the photocatalytic activity and the ERDTCBB patterns. By analyzing those differences, we can, I think we can make the clear discussion on the how the activity is determined by the property of surface or bulk structures.
Okay, I hope the answer will fulfill the Dr. Hendra's question.
Okay, if
So,
you okay, Hendra, if you have a further question, please email me.
yes, indeed. I believe that there is another two question. Please,
Yes.
Professor Otani.
Yes. Okay. I'm not so familiar with XARF, but XPS tell the surface composition and or balance of elements on the surface or surface layers, and that is not limited to outermost surface, but electron trap distribution is reflecting the surface structure, the outermost surface structure. And another important point is even if I had no time to show that, but even if the material is completely amorphous or completely non-stoichiometric one, the ERDT patterns are not so different from crystalline material. Yeah, of course, the some amorphous nature is given in ERDT CBB pattern, but that is not limited to crystalline materials. And it takes a long time to measure. Actually, for example, 3 hours for one sample. So therefore, it is possible to not possible to see the change of structure during the course of photocatalytic reaction. And the atmosphere of measurement is limited to the reductive one, that is methanol nitrogen gas should be uh, in the gas phase on measurement of ERDT-CBB patterns. And the third question, when we can say the materials exactly same each other using this yes, I think it is possible to say that if the ERDT-CB pattern are are the same, that those materials must be the same, and not limited to photocatalytic activity. For example, the some metal oxides powders are used for abrasive, for polishing agent, and that is really the physical property. But if the ERDT pattern the same, the polishing ability is the same. So that means this ERDT pattern is totally identify the product, not limited to the photocatalyst material. And the it is a bit difficult to say how much zeta value is necessary to say that. So actually, that is not the not that is analog one. So in organic chemistry, that is the identification is digital, identical or not identical. But for solid material, that is analog. So the identical, similar, not so similar, different. So that is the analog values, and we cannot say that how much value is the threshold to be to be called identical. But our result tells that if the samples are taken from the same bottle of the same position in the same bottle, that it gives the data value higher than 0.9. Therefore, the temporarily the data value higher than 0.9 gives it is possible to say that that those are identical. Okay.
Okay, thank you very much
I-
for the answer. I believe that your answer will enlighten the Dr. Pramujo and also the other, I think, yes,
okay.
Professor Rossi, I think, yes.
Yes.
The other one, the last one is from Jonathan. Could you answer the question, Professor Ohtani?
Yes. So the important point is if the sample gives the different activity, different performance, different characteristics, those materials show the different ERDT CBB pattern. This is the truth. If the ERDT CBB pattern is the same, they must show the same property, same activity, same characteristics. So therefore, if for example, the one catalyst is used and that is deactivated, if you see those two samples in this technique, you will see the different ERDT CBB patterns. By analyzing the trend of patterns, it is possible. I think it's possible to analyze what is the reason of deactivation and what is the difference in the deactivated catalyst.
Okay, thank you for your nice explanation. So now is the end of the second lecture for this
Thank you
first
very much.
Kembali. Now is the time to give a token to the first and the second lecture, but please let me wrap up the lectures from the first plenary session. The first is from Professor Fiji. It's about the importance of how to harvest the water and the content of the water. For instance, this precious metal and how to manage the water from flooding and etc. And from the second lecture from Professor Ohtani, we saw that the very sophisticated and very sensitive measurement for characterize the catalyst or some compound, I think, and we are very enlightened and we learn many things from this lecture. So I would like to give the tokens for both lectures. This is the token for Professor Vigneswaran. Thank you very much for your participation, and we hope you can also come back and give another lecture in the future, Professor. And the second one is for Professor Bunso Ohtani. This is your token, and we appreciate very much your lecture for today, and we hope also you join another symposium and seminar in the future. You are very welcome. Thank you very much, Professor Fiji and Professor Ohtani. Now,
Thank you very much.
Thank you.
I give back to the committee.
Very very much to Dr. Purwadi and all the distinguished speakers for the interesting talk. I hope it can give us new insights about circular economy and can be implemented to advance our industry. Now, as a token of gratitude, the committee will give a certificate to Dr. Purwadi for being the moderator of today's plenary session. The
Thank you very
certificate
much.
is given to Dr. Purwadi for being the moderator in the Grand Virtual Conference of International Seminar on Chemical Engineering Suhadi Reksa Wardoyo 2020 in conjunction with Symposium on Photocatalysis and Photocatalysis 2020. Thank you very much, Dr. Purwadi.
You're welcome.
Once again, I would like to thank our sponsor and supporters for helping this event to come true. The 2020 STKSR-Symphosis is sponsored by PT Energi Manajemen Indonesia Persero, Kurita Water and Environment Foundation, and PT Rekayasa Industri. This event is also supported by the ITB Chemical Engineering Alumni Association, Badan Kejuruan Kimia Persatuan Insinyur Indonesia, and the ITB Chemical Engineering Student Association. Ladies and gentlemen, may I have your attention, please? Now we have come to the end of today's plenary session. After this, there will be a break for about 10 minutes. Please take a little snack and drink while you can. We'll continue with the first panel session at 10:50 a.m. Participants are expected to fill in the evaluation form through the link that will be provided in the chat room in Zoom. Registered participants are able to join the plenary session, the parallel session through the link that also will be provided in the chat room in Zoom. Thank you.
Thank you very much.
Okay, thank you, Professor Vigi.
Thank you so much.
Thank you, Vigi. So thank you, Professor Otani. So things we will meet again in the future, and then probably here in Indonesia, or it might be in other part of this world. Thank you very much.
Thank you.
Thank you.
Nice of you.
Sure.